We are now beginning the final lecture on material and energy balances, where we have reactions in our processes. So the questions that we would like to ask, and we should be able to answer by the end of this presentation, are: what amount of heat must be added or removed from a reactor process to carry out the reaction to achieve the specified temperature? And we also should be able to calculate the standard heat of reaction when the process is not carried out at the reference temperature of 298 K. And we can also ask, does the standard heat of reaction at the process temperature depend on temperature? So I'm going to be teaching you two different methods. These are also clearly explained in your text book. So I would urge you to read the sections and practice the example problems described in this section. Okay, the two methods of calculation we're going to learn are the heat of reaction method and the heat of formation method. The heat of formation method is the easiest when more than one reaction occurs. At times it is easiest for everything, but sometimes, it just takes practice to know which one will be easier for you to use. So in both methods, we are going to use, and in fact, every case in this chapter, the reference temperature will be taken as 298 K. And that is because that's where we can get the heats of formation. All right, let's start with the heat of reaction method. Now, again, there's two methods here. Don't mix them. You need to follow the instructions so that you don't make a mistake. Okay? All right. So first thing we're going to do, and it's assumed that you know how to do this, from Chapter 4, complete the material balance calculations. Next, we choose reference states for specific enthalpy calculations. And when we have reactions, the best choices are often reactant and product species at 25 degrees C. We are going to use species, molecular species, for the heat, molecular species for the heat of reaction method. And here I have written it. So if you want to follow the heat of reaction method, follow this. Write down these references, molecular species at 25 degrees C in 1 atmosphere. Then prepare your table. All the substances go in the left column. Then we have everything in terms of moles because we have a chemical reaction. We also need to determine the extent of reaction. Okay, and we can calculate the extent of reaction from the moles of A leaving the reactor minus the moles of A entering the reactor divided by the stoichiometric coefficient. Okay, so the extent of reaction should be a positive number. Okay, and then we're going to insert all the enthalpies, which many of them we can calculate. We can calculate many of them from table B.8. However, the ones that are not on table B.8, we are going to have to use the integral of Cp dt. Okay, so now calculate those enthalpies. And again, you may need to calculate, for example, if methane is going in at a temperature other than 25 degrees C, you will have to calculate the integral of Cp dt, and you will find the information for those Cp values on table B.2. Then finally, we will calculate the delta H in the reactor is going to be the sum of the extent of reaction times the delta H of reaction at 25 degrees C, plus the sum of n dot out, h hat out, minus the sum of n dot in, h hat in. Then we will complete our calculation by solving for delta H is equal to Q plus W. Now we're switching directions here. The formation method is different. Again, we calculate the material balances so we can know all of these molar numbers, all the numbers of moles. Okay. Then, now we're going to choose our reference states as the elemental species at 25 degrees C and 1 atmosphere. Elements: carbon, hydrogen, nitrogen, etc. Okay? And then, now, okay, we are going to put here, okay, we're going to have here the enthalpies starting from the elements. So if you have a species like CH4 and your reference state is the elements, first you need to form the molecule of CH4. And how do we do that? What kind of enthalpy are we going to use? We're going to use the heat of formation at 298. And we're going to add that value to the integral of CP/dT. Okay? So how do we do that? Here we go. The heat of formation of the species plus the integral from T-ref, which is 25 degrees C, of CP/dT. Now, notice that when we calculate the delta H for the reactor, we do not include the extent of reaction term that we had in our heat of reaction method. Instead, we only have the sum of n dot out, h hat out, minus the sum of n dot in, h hat in. And I'm sorry, but this should be Q minus W. You knew that. Okay, let's do a practice calculation. And we were going to solve it both by the heat of reaction method and the heat of formation method. Okay, so this one we've already done the material balance on. We've got methane. Methane, 25 degrees C, is combusted with 30% excess air. The air is fed at 100 degrees C and 10 bar with 50% relative humidity. The products leave the furnace at 30 degrees C and 1 bar. Okay, we also have some liquid water coming out. We have water vapor coming out. Okay, so you know how to solve this, except for the part that we don't know how to determine the enthalpy of the reaction process. So let's see how we're going to do that. All right, so these are the values. All I've got put here is A, B, C, and D for each of the species. You can look these up on table B.2. Okay. Why do I have B.8 here? Because you can actually look up this value on table B.8. You don't have to do this whole calculation. You can get the value from table B.8. But you can also do the calculation, as I have shown here. You get the identical number, and you'll see. This is where Excel comes in handy. Okay, but you can't get methane from table B.8, so you have to calculate it. And we're going to calculate it once at 100 degrees and once at 30 degrees. The reference state is always 25, and that's what we put on our enthalpy table. Okay, so we're also going to have the water problem. Okay, to calculate the enthalpy of water leaving the process that has condensed, we need to consider the enthalpy of vaporization. All right, so we can calculate the enthalpy of vaporization at 30 degrees C. We can look it up on the book. All right, and so we get that value, we convert it to kilojoules per mole. All right, and now if we get the liquid value, we take the liquid value, it's going to be the vapor value minus the enthalpy of vaporization at the temperature. Okay, so now you see where I put those values on this table. Now, I know you're confused because you see all these numbers and you don't know what they all mean, but let's walk through them. This one we got from table B.8. This we got from table B.8. This is going to be the water vapor, okay? And we got that value at 25 degrees C. This is our reference state. It has to be when we have chemical reactions, okay? So we got the water vapor value at 25 degrees C, and then we subtracted the value of we added the value of the heat of formation to it. Okay? Now what about the water liquid? We can actually get the enthalpy of liquid water also on table B dot table B dot 1, I think. Okay, so we're going to get those values of heats of formation, and we have one for the liquid and one for the vapor. Okay, so now I've just converted this using the heat of reaction method. We no longer need the enthalpy of formation. Okay, so we calculate our heat of reaction using the stoichiometric coefficients. This is water, this is carbon dioxide, and this is methane. Okay, so we calculate the heat of reaction. There it is. And we calculate the extent of reaction, which is 1. And then we're going to add the sum of n dot out, h hat out, minus the sum of n dot in, h hat in. And we find that in each case, we get the same value of delta H. Okay, so there it is. Now, we have all the water values here are taken from the steam tables. So this is what you should be able to do. Use the spreadsheet to determine the following. What is the heat effect if the inlet gas has 10% relative humidity instead of 50%? Piece of cake. You can do that quickly with the spreadsheet. What is the minimum temperature necessary for all the water to be vaporized? Use goal-seek. What is the degree of error if you were to assume that all the water came out as vapor and none condensed? Okay, what happens to the heat effect if you switch the inlet and outlet temperatures? If the reactor were insulated so that all the heat of reaction is absorbed by the molecules of the system, what would the final temperature be? Again, you can do this using goal-seek. So this is going to be the problem. I'm going to go over the solution to this problem in class because it's too late to give it to you as a quiz. But you can look at it here, take a picture of it and study it and try to solve it. You should be able to solve it. But I will go over it in class.